Let's put the two-sample z-test into the format for hypothesis tests that we've discussed so far. The null hypothesis is going to be that the difference in population means is equal to some particular quantity. Often we say the difference in means is equal to 0 because that's the same as saying the two means are equal to each other, but really what we're saying is the difference in means is equal to some particular value. The test statistic is going to be x bar minus y bar minus mu divided by the square root of the variance of x bar minus y bar. This statistic comes directly from the previous statement that we know the distribution of x bar minus y bar under the null. And so then the reference distribution for the z statistic here is going to be a standard normal, and we get the p-value by looking at the edges there. Now, of course, usually we need to estimate this variance because we don't know the variance in the first population or the variance in the second population. Okay, so there's a couple ways to do that. One way to do that, I like to call the unpooled two-sample t-test. You'll sometimes hear this called Welch's test. The only difference between this quantity and the z statistic on the previous slide is that I've substituted sx squared and sy squared for the sigma x squared and the sigma y squared. That's the sample variance from each population separately. So if we do that, it turns out that technically this quantity right here does not exactly follow a t-distribution, but it's pretty close. So we don't have to worry about the details except that it's pretty close, and if n is big, it looks normal anyway. The reference distribution is approximately a t-distribution, and it'll look like this. There's a slight simplification that's available to us if we believe that the two populations have the same variance. If the two populations have the same variance, then I could take off the x here and take off the y here and factor it out, right? And so then I just need to estimate this one quantity, the overall variance. And here's a formula for doing that via the pooled variance. The idea is let's add together all of the differences between each data point and the mean in its own group, right? So when I take sx squared and multiply it by the denominator of sx squared, what I get is the sum of the square differences for the x group. When I take sy squared and multiply it by the denominator of sy squared, what I get is the sum of square differences from the y group. So altogether, this numerator is the sum of the square differences between each data point and the mean in its own group. And then I divide by the total degrees of freedom, which is nx plus ny minus 2, because I've used up two pieces of information estimating the mean of x and also the mean of y. This quantity right here estimates the variance in each population if I believe the variance is the same in each population. And then I can substitute this SP for pooled squared for this value right here, and that's going to get us the pooled two-sample t-test. And this test statistic looks just like the previous test statistic, except I've factored out those two s's and substituted SP for both of them. Here the reference distribution really is a t, and the degrees of freedom are equal to the denominator of that pooled sample variance. So what are we saying about two-sample t-tests? Here are the assumptions. We're assuming that there's independent sampling both within and between populations. If I choose a particular woman to be in the sample, that has nothing to do with whether any other particular woman will be in the sample. If I choose a particular woman to be in the sample, that has nothing to do with whether any particular man will be in the sample. I'm assuming the two population distributions are normal. This is necessary when we're doing t-tests instead of z-tests, because as soon as we substitute the s for the sigma in that denominator, it's no longer technically true that the reference distribution should be normal. Instead, it should be t, and even then, we need to say the population distribution has to be normal, because the central limit theorem isn't quite enough. As we'll see, though, this assumption is not so important. If we're doing a pooled test, then we are saying that the two populations have equal variances. If these assumptions are not perfectly met, and we'll get more into this, the t-tests are more likely to be valid if the two distributions are approximately normal, approximately the same shape, approximately the same variances, approximately the same sample sizes. All those things help if these assumptions are not perfectly met, which of course they're not. Here's an example of the beak sizes of a bunch of birds, finches, before and after a drought that occurred in 1977. So there's 89 birds from 1976 and 89 birds from 1978. Just looking at these two histograms, it's pretty clear that the beak sizes were larger in 1978 than in 1976, but let's go ahead and do a t-test. We can look at box plots as well. Again, it's pretty clear that the beak sizes were bigger in 1978. I'm not going to go through these details, but I'm giving you this slide so that you can you can have a template for working through the details yourself. Given data sets, you can calculate X bar and Y bar. You can calculate the sample variances and the sample standard deviations. You have the two sample sizes. You can plug those values in to get the pooled sample variance and plug those into the t-statistic calculation to get the t-statistic. And then you can calculate the p-value, which is the probability that a t-statistic with this degrees of freedom would be less than or equal to the t-statistic we actually observed, and that's essentially 0. The t-distribution would never be a value that small. So we say that we have strong evidence contradicting the null hypothesis that the population means are equal because this data summarized by this t-statistic here is really, really surprising if the truth is that the difference in means is actually equal to 0. There's also something called a paired t-test. For a paired t-test, the data comes in pairs. So you don't get to decide whether you feel like doing a paired test or a two-sample test. The format of the data, the setup of the data, the design of the study tells you. If the data comes in pairs, then you have to do a paired t-test. And a paired t-test is something like you have a bunch of twins, and within each set of twins, maybe, I don't know, you look at the education level, and maybe you're interested in whether education level differs within I don't know, a male twin versus a female twin, something like that. What we do is, for each pair, you think about the difference. So the difference in education level for the male twin minus the difference in education level for the female twin. And the assumption is that the average of those within pair differences is equal to some particular quantity, such as 0. As soon as you do that, as soon as you look at the difference within each pair, then it just becomes a one-sample t-test because you just have a sample of pairs. So d bar is the mean of the within pair differences. SD is the sample standard deviation of the paired differences. And then instead of n, we go with the number of pairs. And the t-distribution has degrees of freedom number of pairs minus 1.